You stand at the front of the room and deliver a meticulously refined lecture. You pour 2 decades of experience into it, and the students nod along. Then finals arrive. You read their exam answers and find yourself looking at incoherent statements that suggest they were never in your classroom to begin with. This disconnect happens consistently in the traditional university environment, where an expert transmits information to a massive passive audience. The common response in academia is to blame the audience. We blame a lazy generation, shrinking attention spans, or TikTok-induced brain rot. The reality is anatomical. The traditional lecture format relies on a passive transmission model that is neurobiologically incompatible with how the human brain actually acquires and retains knowledge. To understand the failure rate, we have to look at the brain's biological default setting. Memory is not a passive container. The brain actively and aggressively dismantles neural connections that are not immediately used. This chart shows the Ebbinghaus forgetting curve, a mathematical model mapping exactly how fast information decays when it goes unapplied. Within exactly 1 hour of your lecture, 50% of the new information is gone. By the time students sit for an exam 30 days later, 90% of those meticulously explained concepts have vanished. Being angry at students for forgetting a lecture is like arguing with gravity. If we want them to learn, we have to engineer our teaching around the brain's biological default state, rather than fighting it. Long-term memory decay only accounts for what happens after the lecture. The other critical failure point happens in the exact moment a student tries to understand a complex concept, constrained by a severe biological bottleneck in their working memory. For decades, psychology relied on the assumption that working memory could hold roughly 7 new items at once. Modern studies by researchers like Nelson Cowan have corrected that number. The human brain can hold exactly 4 concepts in its working memory. This limitation is hardwired into our anatomy. Studies on macaques at MIT's Pecauer Institute show that these 4 slots are physically divided. 2 items are processed by the left visual hemisphere and 2 by the right. When a professor puts a complex graph, a flowchart, and bullet points on a single presentation slide, placing 3 or more dense semantic blocks into one visual field, the system is physically overloaded. The learning process halts completely. Intelligent educators continue to cause this overload because they suffer from a cognitive bias that specifically afflicts experts, known as the curse of knowledge. Once you master a highly complex subject, your brain physically loses the ability to simulate the state of a novice's ignorance. You can no longer remember what it feels like to not know the material. In 1990, Stanford researcher Elizabeth Newton demonstrated this cognitive blindness. She assigned people to be tappers, who knocked the rhythm of a famous song on a table, and listeners, who had to guess the melody. When the tapper performed the action, their brain played the full orchestration of the song in their head, but the listener heard none of that context. They only heard a dry, disjointed, and arrhythmic series of knocks on the table. The tappers predicted that the listeners would identify the songs 50% of the time. The actual success rate was 2.5%. Every time you walk into a lecture hall, you are the tapper. When you mention a concept, your brain plays a rich 20-year symphony of research and experience. You assume you are being clear, but the freshman only hears an incoherent, disconnected series of facts. The communication breakdown is a two-way street. While the expert assumes their message is clear, the student is blinded by an equally dangerous bias called the illusion of explanatory depth. This illusion occurs when people confuse their ability to smoothly listen to an explanation with the mechanical ability to reproduce the concept themselves. The Italian designer Gianluca Gimini documented this exact phenomenon with a project called Velocipia, testing how well average people understood the mechanics of an everyday object. When forced to draw a bicycle from memory, the illusion collapses. Participants produced structurally impossible machines with chains connected to the front wheel, unsteerable frames, and pedals hanging in thin air. This is exactly what produces a blank exam page. A smooth, articulate lecture creates a false sense of fluency. The student nods along, believing they understand the mechanics of the subject, and the lack of structural knowledge remains hidden until they are tested. To bypass these colliding biases, education must be treated as an engineering problem. But first, we have to clear the industry of pedagogical pseudoscience, often referred to as neuromyths. The most pervasive of these myths is the idea of visual, auditory, and kinesthetic learning styles. Studies consistently show there is zero empirical evidence that adapting a lesson to a student's supposed sensory style improves their retention. The human brain learns through semantic meaning and structural logic. If you are teaching the spatial geometry of DNA, you use a visual model because the subject requires it, not because a student identifies as a visual learner. If the human brain can only hold 4 items in working memory, how does an experienced professional look at a massive set of variables and instantly know the correct answer without crashing their cognition? Psychologists Chase and Simon explored this by looking at how experts operate in highly complex, standardized environments, like competitive chess. Eye tracking reveals a clear biological difference in visual processing. A novice's gaze is erratic, bouncing from piece to calculate individual threats. The grandmaster's gaze stays centered. They use peripheral vision to recognize massive structural patterns. This chunking mechanism bypasses the memory bottleneck, reducing energy drain. This method of pattern recognition applies to all high-stakes professional fields. It is the exact mechanism that allows an elite expert to spot critical anomalies in milliseconds. A medical student scans a radiograph, looking at individual ribs and empty spaces. A senior radiologist's eyes instantly snap to the specific tissue irregularity the moment the image appears. The psychologist Piotr Galperin argued that we cannot wait for students to develop this expert perception spontaneously through years of trial and error. We have to actively engineer it into their minds. Galperin developed a tool called the orienting basis of action. The core principle is that we must stop handing students perishable step-by-step algorithms and instead teach them to locate invariants. Invariants are the unchanging structural core of a discipline, the speed of light for physicists, or the objective elements of a crime for lawyers. Teaching students to identify these invariants gives them the framework to analyze novel, unforeseen problems. Translating this theory into an actual seminar requires moving the student through Galperin's strict 6-stage roadmap of internalization. You start by generating cognitive dissonance to motivate the student. Then you hand them a physical invariant matrix, a precise visual flowchart mapping the structural core of the subject. The student is required to solve real professional cases by physically tracing their decisions along this printed matrix with their finger. This piece of paper acts as an external hard drive. It completely offloads the cognitive burden, keeping the student's 4-slot working memory clear to process the variables of the case. As the physical matrix is removed, the process moves into the loud speech phase, relying heavily on peer coaching. Students pair up. One person receives a novel problem and must argue their solution out loud, explicitly verbalizing every single logical step from the matrix, while their partner checks their logic. This forced verbalization acts as a physical block against the illusion of explanatory depth. An error can hide in the silent assumptions of a student's mind, but it cannot survive being spoken aloud. Finally, you place the exercise under intense time constraints. The student physically lacks the time to speak every step, forcing the loud speech to collapse into an inner whisper, and eventually into an automated, intuitive judgment. By forcing the complex knowledge entirely outside the head and systematically winding it back inward step by step, you effectively install a localized piece of expert pattern recognition. Even if you execute a flawless seminar using this framework, the biological threat remains. The Ebbinghaus curve is still running in the background, ready to wipe out 90% of these newly formed neural pathways before the final exam. The most common defense mechanism students use against this is passively rereading their notes and highlighting text. This creates a severe illusion of fluency while failing to secure the memory. In 2006, psychologists Henry Roediger and Jeffrey Karpicke isolated the mechanism that actually solves this decay, known as the testing effect. This chart compares 2 groups. Group SSSS studied a text 4 times. Group STTT studied once, then took 3 tests. At 5 minutes, the study-only group led. 7 days later, they plummeted to 40% retention, while the testing group held strong at 61%. The neurobiology is straightforward. The active struggle of pulling information from deep memory without any external prompts physically alters the neural architecture, making the pathway durable. Quizzes, flashcards, and rapid-fire questions are not punitive or bureaucratic assessment tools. They are the single most powerful pedagogical weapon we have against the biological default of forgetting. Delivering a clean lecture is no longer enough. The information is already freely available. To actually educate, we must step away from acting as content transmitters and take on the role of neural architects, engineering the specific conditions required to build a professional mind.